Hyundai's Metaplan uses automated guided vehicles to move pallets between stations, and each pallet must be placed in the correct orientation and at the right distance for the AGV to dock properly. When a pallet is backwards or mispositioned, it causes delays, manual fixes, and unnecessary wear on the equipment. Hyundai's team confirmed that these misloads happen often enough to impact overall efficiency, yet operators currently rely only on visual checks, which aren't reliable in a fast-paced environment. There is no automated system to verify orientation or seating or to log these errors for long-term improvement. This created the need for a fast, accurate, and dependable vision-based solution that can detect misalignment instantly and alert the operator before the AGV moves.
To solve this pallet orientation problem, we developed a whole new system. This comprises of two parts, the main system and smaller substation monitoring systems. That way you can have multiple different pallet loading stations all being monitored by the same more expensive main system with these cheap monitoring system cameras. So what happens is when a pallet comes to the station and is ready to be loaded, the main system will trigger the monitoring system through a Wi-Fi, a data cable, or Bluetooth, which will then take a picture and transmit this data back. The main system, with its more powerful computer, will do different machine learning, AI, machine vision techniques to be able to identify whether the pallet was loaded correctly. We'll talk about this more later. Then, if it was loaded correctly, nothing happens. It just stores the event in its memory. If something failure happens, so it was not loaded correctly, through that same Wi-Fi data cable or Bluetooth, it is then telling the system that it is incorrect, in which case a different warning systems will take place. In our use case, we currently have lights and a buzzer that will play. So as you're looking at these cameras, the actual specifics of the system we've created, we're using an ESP32 for the monitoring system, which has its own camera, an OV5640 with autofocus. And then our main system is NVIDIA Jetson Orin Super Nano, largely because you could probably use a Raspberry Pi, but this is basically we can do a lot of different techniques because of its GPU and a lot faster than on a smaller processor like a Pi. So for actually testing our system and our detection, we have 3D printed a 7.5% scale model of an AGV in a pallet. And we say AGV or AMR, they're both the robotics that move pallets around. So the actual output, the camera that's taken by our ESP32 is sent to the Jetson, which then goes through these processes. So it starts by taking the picture. We have a convolutional neural network, which is a CNN, which we have trained to classify whether a pallet is present on the model or not. One of the things with our goal is we want a 99.9% accuracy. Currently, we have 100% accuracy on our 70 image data set. So maybe more images, it lower, but it is quite accurate from our current tests. Then we use a candy edge filter, which detects to identify basically edges of the pallet and the AGV, as you can see here. We use a huff transform to basically identify the left and right bounds of the pallet to crop. So this is identifying different vertical lines seen in the picture, and then we're using the left and right most to crop. We then take this, crop it, and then all of the subsequent steps are using only that crop region. Then we use we use a segmentation filter, which identifies whether or not there is a yellow marking on the pallet. It's hard to see with this contrast, but there is, and then it identifies the yellow as true. We then use another huff transform, but this time looking for horizontal lines. We take the topmost and the bottommost, which correspond to the top of the pallet and to that indicating yellow line on the AGV, and we're trying to find the difference in angle, because that's our goal, is to make sure these are not angled improperly, because they need to be laying flat and not at a different wrong angle. So some of the failure things that it detects is if there's no pallet. So this is just that CNN and has identified there's no pallet, so we could send the thing warning back to the camera or the ESP32 setup that there is no pallet, so it's in an error state. Another one is the pallet being backwards, which means it's missing that yellow marking. If you notice that there's an F on the AGV, this is like the real setup where they have an F identified in the front. So we can also do, if this particular setup or this pallet loading station has the AGVs facing forward or facing backwards, we can identify whether we are looking for the presence or the absence of that yellow marking for a failure or pass state. And then one of the problems they've had, not super common, but it does happen, is that pallet is not laying flat, so it gets caught on something that's at an angle. We do not have a specific measurement for at what angle it becomes an issue, but we can once that is found out, you can easily implement that into this to figure out if the angle is greater than, say, 1 degree, it's in an error state and needs to be fixed, in which case the lights and the buzzer would go on.
Our solution is innovative because it combines technologies that are usually separated, computer vision, onboard processing, hardware actuation, and long-term data logging, into a single, compact, low-cost system that mounts directly onto the AGV. Instead of relying on expensive industrial cameras, we created a lightweight vision module using the Jetson Orin Nano and Seeed Studio Xiao ESP32S3 nodes. One handles the camera and perception pipeline, while the other controls the alert hardware, including the buzzer and LED indicators, through MOSFET-based drivers we designed ourselves. This makes the system modular, scalable, and far more affordable than traditional industry vision solutions. Our perception pipeline is a dual function. One module detects pallet orientation through market segmentation, and another measures front edge distance with sub-inch repeatability. Everything runs locally and in real time without any cloud dependency, which is essential for a manufacturing environment. The creativity in our design comes from the focusing on reliability and practicality. Every part, power distribution, timing, communications, and enclosure design, was engineered for real industrial conditions while remaining simple to integrate across the entire AGV fleet. The result is a system that reduces downtime, prevents misloads, and brings smart vision capabilities into a process where there haven't existed before.